I'm Michael Robeson.
I'm Christopher Stahl.
And I'm Kent Santibanez. And our research project had to do with vehicle recognition and tracking using multiple cameras. That's what?
Move more that way.
I think it needs a new battery. You have to press it right away.
Do we have it? Okay.
There we go.
Here we go. Well, first we looked at many different research papers having to do using different methods for the way they track different vehicles. And here are some examples using color, metadata, blob, mean shift, and database matching, such. Our goal, well, pretty much, our goal was to try to track a vehicle, a moving vehicle. And well, our uniqueness was trying to track a vehicle where the height changed, as opposed to regularly just tracking a vehicle on their own. So a truly 3D tracking of a vehicle, that was pretty much our goal. Did we get that far? No. Did we actually get to track the vehicle? Yes. But, and here we go. Here are the different, the methods, the steps that we use to eventually track the vehicle. First, we calibrate the cameras, and then we use background subtraction, use blob detection, then draw an outline in that blob and find the centroid in that blob, and that's how we actually track the vehicle. And at the end, the Kalman filter, that's it. This is our video stereo camera setup, 2 cameras, vehicle being tracked on that side. And this was my contribution to this project, trying to find a way to calibrate both cameras that we used. So I searched around and I found this section of a site made by a professor in Caltech who found this information from a paper from other 2 researchers. And pretty much what they did was create a toolbox for MATLAB that allows you to calibrate cameras pretty much. And this site pretty much had all the instructions. That's pretty much what I did, and the way you we went about it was, first we get the toolbox, put it in MATLAB, and then we set up our stereo system, and then we take a video. First we take a video, however our setup was going to be. We record the video, and then at that same point, we take a set of images with with each camera, and this was our set of images. And pretty much what the toolbox does, it does corner extraction. So every picture of the set that we took, pretty much you acquire those corners, and that's how and after you do that, it extracts all the corners. And you do that for every image, on each individual camera. After you do that, you use the results from each individual calibration for each camera. And then you use the stereo calibration section of the toolbox to calibrate both cameras with respect to each other. And that's how the setup went. Set of pictures, 2 cameras, and that's how it detects, how it calibrates both cameras. And that's my part of the project.
All right. So after your cameras are calibrated, you want to actually do something with them. So first you have to acquire video. Now, it's very important. We're recording with stereo, so that's 2 video cameras. So you want your videos to be synchronized. Obviously, if your videos do not start and end at the same time, then your tracking is not correct in any way, shape, or form. So after we record the videos, to get it to work in MATLAB, we had to edit it. You edit to the size you want, edit to the size you want, and convert it to an AVI format. Then, to get it to work properly in MATLAB, we uncompressed it to a raw AVI so that there was no codec issues. And then we import it into MATLAB, each individual frame as its own picture so that you can manipulate every frame. All right, so the process of tracking the vehicle is, first we acquire the video, we change that image into grayscale every frame, we apply a background subtraction, which it takes a mean value of every 100 frames. It looks at it to see what's changed between, and the constant, what isn't changing in the images, gets subtracted out to the base values. So the car that is moving stays within the pictures and everything else gets subtracted out. Then we use a blob detection algorithm, which will detect a moving blob throughout all of the images. It draws an outline around that, which it draws an outline by calculating the area, and then it plots the centroid on that outline, which that would be our original video. You can see nice little car moving across. We changed it to grayscale. Then after the background subtraction, you can see how all the background gets out. You just have the vehicle. And it outlines it in a nice yellowish green. And then finally, you can see that blue centroid stays constantly marked on both. Alrighty.
All right. Well, my part of the project had two parts. The first was actually filtering the data. I used a basic Kalman filter at first. This was just kind of get a baseline of what we were going to do to begin with. So the basic Kalman filter is a simple linear filter, and I use this for a couple of reasons. It was easy to implement. Dr. Chen had a little bit of knowledge and gave us a presentation in the beginning and helped us with this. It actually also helped us to smooth out data inconsistencies. A lot of the times we would take images from the two separate frames and they wouldn't exactly sync up. They would be one frame off. And so by going back and using the Kalman filter on these inconsistencies, we could get them to be a lot more smooth and a lot more accurate. Also, I tracked each dimension separately because I ran the Kalman filter both before doing the 2D and the 3D and afterwards to see which produced better results. And when I did it in 2D, I was obviously only tracking 2 dimensions, whereas in the 3D I was tracking all 3 dimensions. So I made it flexible in that way. I also implemented it in separate dimensions so I could vary the error on each dimension separately because our depth was a lot more finicky due to calculations since it wasn't actually measured right from the picture. We had to calculate it using external parameters. So using the Kalman filter, I was able to track a cube in 3 dimensions, which I'll go show you a picture on the slide after next. First, guys, I want to give you a quick idea of what the Kalman filter looks like. This really is the entire Kalman filter right here. There's 2 separate sections. The first is the time update section. Basically, this takes the previous step and then incorporates it and brings it up to the current time. This updates both the X estimate, basically, if you were at, say, position 1 at time 1, it now says you're at position 2 at time 2. This also updates the error from the previous time. And then there's a measurement update. This says if we have a basic model and we expect you to be here, but our measurement says you'll be here, it kind of takes an average of these two and calculates what our best fit position will be. We also update the Kalman gain, which gives us where we think the point will end up, and we also update the error at this section as well. There we go. All right, so this is the cube I tracked in 3 dimensions. It basically moves. It's got a slope of 1, 1, 1. So it's just moving straight up. There are 8 points, and you can kind of see how it's tightly bunched. I fed the Kalman filter some random data with Gaussian noise in it, so it wasn't exactly a pure cube, and it didn't track it exactly. So you can kind of see it as it moves up in the curve, and you can see the linear motion that's been tracking. So after I implemented that basic Kalman filter, I actually moved on to extended Kalman filter. The reason for the upgrade was our final model was going to be nonlinear. The car doesn't just move forward, it moves back, it moves up, it's down, it moves left and right. This way we need a system which can approximate a linear system because our final project is not actually going to be a linear system. The car doesn't move in a straight line. It can do all sorts of things. So this is why we use the extended Kalman filter. Another advantage of using extended Kalman filter, and like I talked about earlier, was the separate axes, was that I could adjust the different noise parameters separately. I adjusted the measurement noise, process noise, and the different model parameters for each axis to track them separately. Like I mentioned earlier, the z-axis was very, very finicky and could jump up and down, so I tried to modulate that a little bit more than the x and y, which we drew directly from the pictures. So this is kind of an example of what the difference is between the extended Kalman filter and the regular Kalman filter. I've kind of highlighted the differences. Instead of using matrices, which you multiply by the previous data, you actually use functions which take the previous data and then use some sort of nonlinear calculation to update it. This is found in both F and H. And then also you have the two Jacobian matrices W and V, which are used to update the error and the Kalman gain, since you're updating these at every step and it's not linear. All right. So after I finished the filtering part of the project, I moved on to stereo equations. Since we have two sets of pictures, we can use some stereo formulas to actually calculate the three-dimensional position of an object by using the differences in the two different pictures and some information we know from the outside world. So we use three set of equations to calculate these. We take the data I have from the Kalman filter and then we run it through these equations so we get a real-world movement, and I'll show you later on what it looks like when we actually run it through here. So if we go back to our initial setup, this is what it looks like, and you can see here we have our two cameras, which are the two blue dots, and then you have the blue dot, which is where our point of the centroid is right now. You can see how the similar triangles measure. This is the focal length here and here, which is the same, and versus x2 and x1, which are the pixel distances, are the same triangles made by the z distance here, and then the x2 and x1, which are the real distances. So using this setup, we can calculate both the depth of the vehicle and then its position on the x plane as well. And then also, if you turn it, say if you had a y-axis which was coming out, you would have the same sort of similar triangles for the y-axis. So using all that, we were able to generate a tracking algorithm which would actually track our car. This is kind of the sum total of our project right here. As you can see, it starts over here and moves. It actually moves farther away according to the algorithm, but then moves kind of along the x-axis down here. Very little variation on the y-axis. I'll show you a better view here of the y-axis, basically straight on. So you can see how our y-axis, there's very little variation, probably not even an inch, probably half an inch, which is exactly what we were looking for. The y-axis in our project was how far away the car was, or how left and right the car went. And it didn't, for this particular one, we kept it on a straight line, so it only moved on the x-axis because that's what we wanted to highlight for this. So you can see it's very little variation, which is what we were looking for. Now if you look at the x and z axis, which will be on the next slide, you can see how the car moves from about 10 to about -18, which is a 28-inch movement total. Actually, we went back and measured it. It was about 26 inches. So our performance was pretty good, kind of what we expected. One kind of alarming or problem we had was the huge jump in the Z here. You can see how it goes from almost 40 to about 50, the 10-inch jump. This is due to the fact that when you drive a car close to the middle of the cameras, the distortion caused by the two cameras actually gets you inaccurate measurements of the X and the X1 and the X2. And so using the calculations between these two actually produces some inaccuracies in the Z value. I also talked about how we had frames that weren't exactly completely synced up because it would move forward in one frame and not in the other. Not because the time wasn't the same, but because just how the cameras operated. So this inaccuracy also causes Z value to be a little larger than expected as well. So those are our results. If we were to have a little extra time to work on this project, some possible ways we could go with this would be to estimate the velocity of the moving vehicle. This wouldn't be too hard since we already know the place it is at the place it is at time 1 and time 2. We can incorporate this in. This is actually a part built into the program already. It's just an aspect we haven't highlighted. We can also estimate the velocity of a moving vehicle. This is a lot more difficult because you don't necessarily know how the vehicle is going to move. But if you did have a pretty good idea of how it would, you could actually get the acceleration. Also, some ideas that just kind of came up to us were that we wanted to expand to detect multiple vehicles. Currently only driving one single RC car. You saw the picture, it was just kind of a single frame. But we could expand this to detect multiple blobs that had different spots, kind of like one of our other groups was doing. And so we could track 2 or 3 vehicles in 3D space at once. And also we could detect possible collisions if all these parts were to come together and we were to detect multiple vehicles with their velocities and their accelerations. All right. So there's our bibliography. We'd like to thank Dr. Demetrios and Dr. Chen and the REU hosted by the UNO. And are there any questions?
Did you use a ramp or anything to actually change Z and see if...
No, we actually did not get around to that. The computer would not turn on the last couple weeks, and then the day before we were actually going to present, we actually figured out that the socket was dead and finally got it working, but by that time it wasn't quick enough that we could get in the process and fine-tune everything so it worked. So we were trying to, but it just kind of fell apart due to hardware failures at the last minute.
You and no equipment.
Yeah. Surprise.
Okay.
You have the calibration results for the two cameras on that experiment where you run the extended common filter.
Do we have the results?
Yeah, for the calibration parameters.
Yes.
Because it seems that you need that to
Run the common.
implement your extended common filter.
Yeah.
Well,
Yeah.
what
Yes.
are the like focal length, external?
We have the. Or do you want?
There's a file automatically created by the calibration toolbox where it gives you everything.
Yes.
So
Yes,
you
we
know
do
roughly
have.
like the focal length in that experiment?
I want to say it's like 40, but I don't know for sure.
Because you said that when the vehicle approaching to the two cameras,
Yes.
you'll have some distortion because the pinhole camera model may not be accurate
Correct.
at all. So,
Yes, now, I don't know exactly what the focal length is. It was the same for both cameras and in both axes.
yeah, and they're looking at the same direction.
Yes.
Where you have these two.
Well, they're actually slightly offset because it's very difficult to line both the
Yeah.
cameras
Okay.
correctly, like exactly straight. We tried to do our best as we could and line them up as much as possible, but
With
they're
the type
slightly
of camera we
turned.
have to get them perfectly, it's not
Yeah.
feasible.
And even the paper said when you have that overlapping field of view and it gets close to both the middle of the cameras, because it's in the middle of the camera, they lose kind of a bit of definition, and so there's going to be some distortion caused by that.
Okay.
Yeah.
And you know like the camera location approximately or?
Yes, I mean, well, the vehicle location is relative to the camera.
Yeah.
The right camera is 0, 0, and then we know the distance between the two cameras. That's, I should have mentioned that, it's a central thing we have to know. The focal length and then the distance between the two cameras, we input that into our program, and then from that we can generate, let's see if I go back to it. The one slide has the pictures of the cameras. So this distance is known, and we have to know this distance, and then we have to know the two Fs in order to calculate all the other values.
Okay, and also you need to know the left side of the camera, right? Where the camera is pointing at.
Yes. Mm-hmm. Yeah. All right. Any other questions? All right. Guess that's it.